Good afternoon, and thanks for the introduction. And I'm Yupeng Li, and from the University of Hong Kong, and I'm under the supervision of Professor Francis Lau and Dr. Haisheng Tan. And today I'm going to talk about efficient online Coflow routing and scheduling. So let's look into the motivations first. Applications in this era always consist of a communication stage and a computation stage. And the computation stage becomes more and more important, especially for the application's performance. So for example, Facebook analytics jobs spend almost 1/3 of their runtime in communications. And we, as the system designer, could no longer ignore the effect of the communications, which means we need to optimize the communications performance. So we observe there are a bunch of significant works on optimizing the communications performance, and among them, the individual flow scheduling is likely to be one of the most significant ones. So with individual flow scheduling, we sort of want to minimize the flow completion time. But could we really benefit from it? I mean, we also as the application user may care about much of the user experience, such as the response time of an application and the completion time of an application, and etc. So our question becomes could we really improve our user experience with individual flow scheduling? As you may expect, the answer will be not exactly. And next, I will use an example to illustrate the reasons. So here comes to our situation. There are two applications, C1 and C2. And each application has two flows running on two links, link 1 and link 2. For application C1, 2 units of flow is running on link 1. And 4 units of flow is running on the link 2. And on the other hand, for the application of C2, 4 units of flow is running on link 1, and link 2 has 2 units of flow. And so obviously, each link has a capacity of 1 unit per unit of time. And here, our goal is to minimize the application's completion time. So very naturally, we can find that the application's completion time is determined by the last flow to complete. So here we go. If we use the max mean fairness, which is a well-known individual flow scheduling approach, so on each link, during the first 4 units of time, we kind of enforce the max mean fairness among the 2 flows on each link. So by doing so, both applications will end its transmission when the time reaches 6. Okay? So here we use the average CCT, which is short for Coflow completion time, to evaluate the performance. So therefore, the maximum fairness can achieve the average completion time of 6. So here is another approach. Called flow prioritization, which is also a well-known individual flow scheduling approach. And basically, it prioritizes the flow on each link with the smaller size. And by doing so, the performance is the same as the max mean fairness. And the flow prioritization approach can achieve the average completion time of 6. So what about the optimal? Here, this figure shows one of the optimal scheduling. And on one of the links, say link 1, we kind of enforce the max mean fairness among the 2 flows. And on the other link, we kind of prioritize the flow with larger size. So by doing so, we can, one of the applications, say the application C1 can end when the time reaches 4. And the other application can end when time reaches 6. So let's see the performance. The optimal can achieve an average completion time of 5. If we move back to compare the optimal with the individual flow scheduling approaches, we can easily find that the reason for the individual flow scheduling approach does not perform very well is that they kind of ignore the joint effect among the flows on different links, but which these kind of flows may come from the same application. So to bridge this gap, the Coflow abstraction is proposed by Chowdhury and Stoica from MP Lab. And basically, the Coflow connects the application and the networks to express the requirements of the applications in the networks. And to be more specific, the Coflow is a collection of flows who share a common objective. And again, the completion time of a Coflow is determined by the last flow to complete. So our aim becomes to minimize the Coflow completion time. And there are some significant works on Coflow scheduling, and the corresponding literature is listed below. And some of them focus on designing efficient heuristics, but such heuristics has no performance guarantee. And some of them consider the offline version of this problem, which seems impractical, as it is always very difficult to acquire or, in other words, to predict all the Coflow's information. And the majority of the existing works assume a non-blocking switch to model the network, and routing indeed matters. So here comes our settings and problem. And here's our settings. In a network, Coflows always arrive at different time. And we hold no other assumptions on the Coflow's arrival. And secondly, flows within a Coflow always arrive simultaneously, and this is suitable for most of the scenarios. Therefore, our problem is to design an online algorithm to find a valid routing and scheduling strategy for each Coflow so that the average CCT is minimized. Here, CCT is short for Coflow completion time. And I want to add more words on the words online and valid. Online means that the information of a Coflow is given only at its arrival, which means we have no prior knowledge of the subsequent Coflows. And valid here implies the constraints of the network and also of the Coflow should be met. So different from the aforementioned literature, our goal mainly incorporates three parts. And firstly, we need to handle the competition for the transmission resources. And there may be multiple Coflows running the network concurrently, right? And when we look into one of the Coflow, there may be multiple flows, which means we need to handle the inter-Coflow interaction as well as the intra-Coflow interaction. And here, the resources are basically the flow paths and the bandwidth. Secondly, we want to consider the more practical online version of this problem. And here's one of our observations. And the offline Coflow scheduling, even with no routing, is proved to be NP hard. And this is done by reduction from the well-known concurrent open shop problem. And again, online means that we have no prior knowledge of the subsequent Coflows. Finally, we always want to design a scheme with performance guarantee, which means we need to do worst case analysis and then to derive a non-trivial competitive ratio. So here comes to our solution. We first look into a special case where there's only one single Coflow in the networks. And this is actually the aforementioned intra-Coflow scheduling and routing. And we design an approximation algorithm called Untitled for this case. And then we let it be a black box and to further design an efficient online algorithm called OMCoflow to handle the more general case, which is actually the Intra-Coflow scheduling and routing. So next, let's first look into the Intra-Coflow scheduling and routing. When there is only one coflow monopolizes the network, remember, our objective is to minimize the coflow completion time. And this problem can be formulated by the mathematical programming, which is actually a mixed integer non-convex program. So we focus on designing the approximation algorithm to tackle this problem. First, we relax the original program to a continuous variable one, and then we have this program P. In this program, the variables are the flow bandwidth, which is denoted as Bj, and where J is actually the flow ID. And xjp is also our variable, which denotes whether we select the path P for flow J. And finally, our variables include the flow completion time, and which is also our objective, which means that the flow completion time is also the coflow completion time, and I will explain it more later. So these constraints can be derived following our settings. And the constraint A is actually the link capacity constraint. And the constraint B, C, D is actually the flow path constraint. And here, we allow each flow to use only one path. And finally, the constraint E is actually for flow completion. And here, we kind of play the trick, and we enforce all of the flows within one coflow to be completed simultaneously. And know that this is not harmful to the coflow's performance, because remember, the coflow's completion is determined only by the last flow to complete. We further design an approximation algorithm called Untitled to tackle the Intra-Coflow scheduling and routing problem. And for the program P, we find that if we fix the time t, the flow completion time t, and the program P becomes to be an LP. So we can binary search the t by showing several feasibility LPs to obtain an optimal for the program P. And remember, our original problem is the integer programming. So we further design randomized algorithm to run the variables. And after the randomized running, we further scale the flow bandwidth and this is to make each flow to be feasible. And secondly, this is to fully utilize the link capacity. So here's the framework of Untitled. And the input for Untitled is actually the information of Untitled C, includes the volume and the source and destination pair of each flow. And the output of Untitled is mainly a valley strategy, which is denoted as the bandwidth B and the path P for all of the flows. And during the computation, Untitled also outputs the optimal value for program P. So after the analysis, we show that Untitled can achieve a forlorn 2n approximation ratio with high probability. And here, n is actually the node number in networks. So next, let's move to the Intra-Coflow scheduling routing. And remember, we consider an online environment, and we design an efficient online algorithm called OMCoflow to tackle this problem. And basically, the OMCoflow make use of the one coflow as a black box. And the basic idea is that when a new coflow arrives, or an existing coflow finishes its transmission, and we will reschedule the flow bandwidth for all the concurrent existing coflows. So to be more specific, remember the OPT is the optimal value of program P, and program P is relaxed from the original program, and we base on the optimal value for each of the coflows and compute a scaling factor for each of the coflows, and following this formula. And in this formula, the capital I is actually the set of all of the concurrent running coflow. And based on this scaling factor, we can scale up or down the flow bandwidth for each of the coflows. And by doing so, this is kind of a weighted combination of the single coflow scheduling and routing. And here, the weight is basically the scaling factor for each coflow. Okay? So here's the framework of OMCoflow. Again, the input are the coflow information, and we first assume each coflow monopolize the networks, the whole networks. And by one coflow, we can compute for each coflow a valid strategy, includes the bandwidth and the path for all of the flows within this coflow. And by the way, during the competition, again, the one coflow will compute the OPT value for program P, which is relaxed from the original program. And then based on this optimal value, the OMCoflow further computes a scaling factor for each of the coflows. And based on this scaling factor, OMCoflow reschedule the flow bandwidth. So ultimately, the OMCoflow will output the bandwidth and the path for each of the flows. So through analysis, we show that OMCoflow can achieve 4M ln 2n competitive ratio. And here, M is actually the number of the concurrent coflows. Here, we want to show some advantages of the OMCoflow. Firstly, OMCoflow will route each flow only once, which means that there's no frequent rerouting. And we observe that frequent rerouting may incur overheads in real systems. And secondly, OMCoflow is work conserving, which means that it fully utilizes the network capacity and at the same time to minimize the coflow completion time. And thirdly, OMCoflow is starvation free. And in our problem, we allow bandwidth preemption. So by OMCoflow, there is no coflow starving at any time. And finally, OMCoflow is performance guarantee. And OMCoflow is actually a competitive online algorithm. So here comes our experiment. In our experiment, we used the workloads from Facebook production, which is based on a Hive MapReduce trace. And we use this workload to conduct experiments. And in our experiments, we compare our algorithm, the OMCoflow, with the state-of-the-art coflow scheduling only heuristic, and the state-of-the-art heuristics for coflow scheduling routing. So through extensive experiments, we can find that OMCoflow can reduce the coflow completion time by 41% almost. Moreover, OMCoflow is with less runtime when comparing to the state-of-the-art heuristic tackling the same problem, which means that OMCoflow is more scalable. So to conclude this talk, we show that OMCoflow is the first scheme tackling the online multiple coflow routing and scheduling problem. And more importantly, OMCoflow has performance guarantee. And here are some key issues that we want to consider in future. And first, what if the flows within one coflow do not arrive simultaneously? And second, we observed that recently there is some significant works on reducing the overheads of rerouting. So what if we allow coflow rerouting? And finally, in our problem, we allow each flow to use only one path. But so what if we allow multiple paths for one flow? Okay, and this is the end of the talk. And thank you for listening.